a little bit about graphing and then the context of 17b. My graph doesn't need to be perfect. Really, I kind of just need to know who's on top and who's on the bottom. So usually it's enough to know, especially if I've got a line and a parabola, all I really need to know is the parabola point up or down? Does the line have a positive or negative slope? So if I were to put these two things together and not worry about where they were on the axes, y equals x squared, well, that's a concave up parabola. And y equals 6 minus x is some sort of line with a negative slope. So it's going to cut through something like this. So without doing any more work or any more detail on the graphing, I know that if I draw in an arbitrary cross section that's a rectangle, I know what's going to happen here. I know that the function that's on top is the equation of the line. And if I subtract off the function that's on the bottom, the function that's on the bottom is the x squared part. Now I just need to figure out how far to the left and how far to the right to push those cross sections. And to do that, I'm looking for the intersection point. So to find that intersection point, I can set the two equations equal to each other. I like to factor with a positive x squared, so I'm going to push everything to the right and say that's 0 is equal to x squared plus x minus 6. This one happens to factor. If it doesn't, that's okay. We have tools. We can use quadratic formula if we've got some sort of quadratic. So in order to get that negative 6, I know it's going to be a 2 and a 3 because I've got a plus x in the middle. I need that to be a plus 3 minus 2, which tells me that these are going to intersect at negative 3 and positive 2. And those are going to be my limits of integration. Negative 3 goes on the bottom, 2 goes on the top, because I would push these as far to the left over here as negative 3 and as far to the right as x equals 2. Now we're doing fundamental theorem of calculus. Find the antiderivative, plug in the endpoints. My antiderivative here, I'm looking at 6x minus 1/2 x squared, or x squared over 2, however you want to write that. Minus 1/3 of x cubed. And we are going from negative 3 to 2. I'm going to plug in a 2 everywhere and then plug in a negative 3. I get a lot of questions about how much do you need to simplify? My answer is not. Really, we just need to plug the numbers in. If you want to simplify it, my recommendation is to look for things that already have common denominators. So I'm going to plug in my numbers here. So when I plug in the 2, 6 times 2 is 12. 2 squared would be 4. Half of 4 is 2. 2 cubed is 8. So I'm going to have 8/3. From that, I'm subtracting off. When I plug in negative 3, 6 times negative 3, that's negative 18. Negative 3 squared becomes a positive 9. So that's minus 9/2. Negative 3 cubed is negative 27. Times 1/3 would make that negative 9. And then minus the negative would make this plus 9. I always check and see, hey, does anything already have common denominators? No. If I were going to do some simplification, I would at least add up and deal with the whole numbers and distribute the minus sign through, even if I didn't clean up the fractions. So I'm going to do that kind of all in one step. Negative 18 plus 9 would be negative 9, but it's a minus. So I'm at positive 9. And I'm just personally going to give myself something to note that I've already dealt with those. So I'm at plus 9. 12 minus 2 is 10. So I've got a 10 plus a 9. So that's 19. Minus 8/3 minus a minus will make that plus 9/2. And personally, I might genuinely just leave it there. If you wanted to get a common denominator, 6 is going to be our common denominator. Yeah. Sorry, this step, this part. So I didn't tell you what the bounds were going to be for integrating. So we needed to find what numbers create the bounds for the region. So we're looking for the region between these two. And so I need to know where they intersect to figure out what the bounds for that region are. Yeah. I'm going to put on my trig pre-calculus kind of hat, and I'm going to start with the y equals sine of 2x piece. Now that 2 inside of my sine changes the period. So when I look at this function right here, the normal period for sine of x or cosine of x is 2 pi, but with a 2 right there, I'm going to get the period by 2 pi divided by that coefficient on the x. So the period is now going to just be pi. So that means my sine graph has to complete a full cycle in pi. Get this up just a little bit more. Okay, I'm gonna try to get this going here. So I'm not very good at making perfect trig graphs, and the way that I like to cheat is to draw the curve in first and then put in the bounds, because otherwise I will never manage to squeeze that perfectly into whatever I deem to be pi. Some people like to do it by graphing points, but I'm just going to draw a sine curve, do my best to make it symmetric, and then declare that to be pi. By the way, that means that right here in the middle, that is pi over 2. So now I'm going to put onto that the cosine graph. And I know that both of these go as high up as 1 and as far down as -1. Cosine starts at the top and cosine completes a top to bottom, back up to top in 2 pi normally. But since I'm only have my graph going to pi, my cosine graph has to go just from top to bottom. That's all I've got to get to for cosine. And then I'm going to look at, really, we're only caring about the portion from 0 to pi over 2. Now, you all have heard me say this a lot. I'm always going to choose to get partial credit first. So right now, I can already put a whole bunch of stuff down on my paper to be getting partial credit, even before I figure out what that intersection point is. So I'm going to go ahead and score my partial credit points. So I don't know what this point is. I'm just going to leave it alone for now. I actually do know what the point is, but I'm going to leave it alone for now. We'll solve for that in a second. So in this first region, I know I'm going from 0 to whatever that is. And in this first region, if I draw in my arbitrary cross section, the function on top, I know it's a little hard to see the color difference, but my function on top is the cosine. So this would look like cosine of x minus sine of 2x. My other region, I'm going from whatever that x value is to pi over 2. And over here, if I draw in my arbitrary cross-section, the sine of 2x curve is what is on top. That's a whole lot of partial credit without really having to do the messier trig part. But now let's get into the messier trig part so we can figure out where that intersection point is. There may be other clever ways to do this. The only thing I know how to do is to use a trig identity. Calculus cannot change the argument of a trig function. Calculus cannot help me turn a 2x into an x inside of trig. Only trig identities can help me do that. So if I try to set cosine of x, by the way, if you have all your trig values memorized, you don't even have to do this step that I'm about to do. If you have all of your trig values memorized, you might already know that the angles that kind of work in a pair with sine and cosine are pi over 3 and pi over 6. So if you've got your trig memorized, we would already know that that's pi over 6. But if you don't, here's a way to get back around to that. If I try to set cosine of x equal to sine of 2x, I can't solve that while the arguments inside are different. But we have a trig identity for sine of 2x, and sine of 2x is equivalent to 2 sine of x times cosine of x. If I subtract the cosine over, I can now factor out a cosine. Meaning I know one of my bounds is going to be where cosine is equal to 0. That's the pi over 2. And my other bound is going to come when sine of x is equal to 1/2. And that's going to give me that pi over 6 angle. But in the end, you have to memorize something. There isn't really a way around that last jump of knowing what angle this is going to work for. If you got this far and you still were like, I don't remember, is that the pi over 3 or the pi over 6? I always fall back on drawing an equilateral triangle. All the sides are 2. So when I cut it in half, that side is 1. And since it was an equilateral triangle, I know that angle was 60 degrees or pi over 3, which makes this side that we cut in half the pi over 6. So now I know that these should be pi over 6s. We can finish off the integration. Did you all want to finish off the integration together? Or did this get us far enough? Got us far enough? Okay. Squared is going to hit at 0, 0. 5 minus x squared is going to be up 5. Oh no, graph was accurate-ish. It's going to be up 5 and curve down. We're okay. Okay. So we're talking about this region here. I did okay with my graph. We're going to spin that around the x-axis. For those of you that may have had calculus in a previous life, you may have learned other methods for finding volume. Sometimes we talk about something called the shell method. We are not touching that in 17B. If you've got friends taking the 21 series for calculus, they might see it there. You might even have a TA or someone in the calc room try to show you another method. It's not the method that we use for 17B. So for 17B, the only thing we're looking at are, sometimes we call them washers or discs. Lights went off in the classroom for no reason at all. That's fun. So what I'm going to always do is draw my arbitrary cross section and work from there. If I'm spinning around the x-axis, then the arbitrary cross section that I draw needs to be a rectangle, kind of like that. And when I take that rectangle and I spin it around in a circle, kind of looks like a really flat donut or a washer. And when we're talking about that volume, I think about this as a big volume minus a little volume. And what happens when I spin that around in a circle is we end up with a circle that's got a little bit of thickness, which we could also call a cylinder. Define the volume of that circle with a little bit of thickness. I'm looking at the area of the circle times a little bit of thickness. And in this case, my little bit of thickness is a dx. If I'm spinning around something and I'm spinning around one of the actual edges of the shape, then when I rotate that around, there won't be a hollow part in the middle. But if I spin around something that is not one of the edges of the shape, then when I spin it, I end up with a little bit of a hollow part. So we're going to subtract off that little bit of hollow part that we get. And I've labeled these like a big R and a little r. My picture I made really small, which is unfortunate. So if I kind of blow this up a little bit and just look at the region we're talking about, when I draw in that arbitrary cross section, I've got a small radius and a big radius. I'm always going to measure my radius from the axis of rotation until I hit the curve. So for my big radius, I start at the axis of rotation and I go up until I hit the curve, the farthest most curve, and that farthest most curve is the 5 minus x squared. So this part, I'm going to have 5 minus x squared, whole thing squared. For my inner radius, I'm going to start at the axis of rotation and just go until I hit the inside curve. And that inside curve is the 1/4 of x squared. So I'm going to have pi times 1/4 of x squared times the little bit of thickness. Tons of partial credit there. Now let's get the rest of our points by figuring out where they intersect. So if I set those two equal to each other, and I've got 1/4 of x squared plus 5 minus x squared, you have choices. If you don't want to deal with fractions, multiply the whole thing through by 4. I'm going to go turn the light on because I feel like it's dark in here. Better. It's kind of slightly gloomy outside. I need a little more brightness in the room. So I'm going to choose to multiply everything through by 4. You don't have to do it this way, but now I can add my x squareds over. 5x squared is equal to 20, or x squared is equal to 4. So my bounds are going to be plus or minus 2. Which means both of these are going to go from -2 to +2. In terms of actually evaluating this, be careful to actually FOIL this one out. That's 5 minus x squared times another 5 minus x squared don't make the careless mistake of just squaring each piece. Do we want to finish this one off together? Yeah. So, it all comes down to the shape of the object. So, because what I'm rotating around is not one of the edges of the object, if I were to spin this around, I would kind of get another copy of it over here. So it would almost look like a bead. It doesn't quite have a hole in the center, but it sort of has these cones almost cut out of the ends. And so this portion back here is just like cutting that piece of the cone out. If instead I were looking at something like maybe here's y equals x cubed. And maybe I looked at this region and I rotate this around the x-axis. Because the axis of rotation is actually one of the sides of the piece, each slice will just look like a circle with a thickness. It won't have a part cut out of it, if that makes sense. These can be really tricky for folks to visualize, and I am not the best 3D artist. So because of that, I really rely on knowing, is the axis of rotation actually one of the sides of the region? And if it's not one of the sides of the region, then there's going to be some sort of piece that's hollowed out. Did that help a little?
Yeah.
Okay. You're welcome. Other questions about this one? Yeah.
And so the second part of the integration, so that part is the hollow, representing the hollowed out part.
Mm-hmm. It is okay to put these into one integral. Like, it's totally fine to have this written as -2 to 2 of 5 minus x squared squared minus 1/4 x squared squared dx. If you want all of it to be in one big integral.
So that's just like the outside circle minus
the inside. Yeah.
And that goes for like any shape that uses the like a radius.
Yeah. So if I'm revolving around something as opposed to taking slices, so like on homework 10, question 3, the slices are squares as opposed to revolving something. But anytime I'm revolving something, this is really the format we're going to have. But if I revolve around an edge of the shape, we sort of don't have the subtracting part. Do you want me to make another one up, or do you have another one on?
Oh, no, I was just saying.
Oh yeah, we can totally finish it. So if I'm going to finish it, I need to multiply this out. So 5 minus x squared times another 5 minus x squared. That's 25 minus 5x squared minus another 5x squared plus x to the 4th. And if I square this piece, that would be minus 1/16 x to the 4th. Remember, I haven't integrated anything yet. That was just me doing the algebra we needed to make it look like x's raised to powers. Scoop this up a little bit. You can choose to combine things at this point or not. Sure, let's combine things. So I've got 25 minus 10x squared plus 15/16 of an x to the fourth. So finding those antiderivatives, I've got 25x minus 10/3 x cubed plus, I'm going to do fraction math in my head here. When I add 1 to the exponent, I'll be at 5. And when I divide by 5, 15 divided by 5 is going to leave me with 3/16 x to the fifth, going from -2 to 2. And I don't want to forget my friend pi. He's chilling over there. Am I doing okay so far? So when I plug in 2, that's looking like 50 minus 2 cubed, that's 8. 8 times negative, so 80/3. 2 to the fifth is 32. I'm going to go ahead and divide that by 16 because then I'll just have 2. 2 times 3 is 6. Minus, and I plug in -2, 25 times -2 is -50. -2 cubed is -8. That minus and that minus will make this a plus 80/3. -2 to the fifth is -32. Divided by 16, I'm at -2 times 3, so that's a -6. And if we want to keep going, by the way, I think you're fine to quit there. But if you want to keep going, to simplify this a little bit more, I would at least distribute my minus sign. And this is definitely a case where I have two pieces that already have a common denominator. At least put them together, right? So that's a 56. And when I distribute the minus signs in, I have another 56. 56 and 56 is 112. And then -80 and a -80 is a -160. I'd probably quit there. Although 3 times 112 is not so bad to get a common denominator on. Sure. Draw my arbitrary cross section, figure out what the radii are, and go from there. Natural log of x. He's our friend. We should know how to graph him at this point. We've been playing with natural log of x for a while. So here's natural log of x. Got that one graphed. X equals 0. We just have to take a minute to remember that x equals 0 is secretly the y-axis. And then we're slicing through at y equals 1 and y equals 2. Since we are rotating around the y-axis, when I draw my arbitrary cross section, it needs to be perpendicular to the axis of rotation. So if I'm rotating around the y-axis, my arbitrary cross sections have to be horizontal so that they're perpendicular to the axis of rotation. So here's my arbitrary cross section. And I'm going to revolve that around the y-axis. So it's going to spin around in a circle. By the way, the axis of rotation is one of the sides of my object. So I don't have a part to subtract off. So when I do this, I'm just going to have a single radius squared times the thickness. And because I'm rotating this around the y-axis, because my arbitrary cross section is drawn horizontally, my little bit of thickness is dy. And that right there dictates the rest of the problem to me. So if my little bit of thickness is dy, that's the variable that I'm integrating with respect to. So it means that my bounds, my upper and lower bounds, have to correspond to the y values. So the y value at the bottom of my shape is 1, and the y value at the top of my shape is 2. The next piece I have to figure out is what's the radius. I draw my radius from the axis of rotation until I hit the function. So I start at the axis of rotation and I'm going to go until I hit the function. So the function that I hit is natural log of x. But there's a problem. My integral has to be in respect to y. My bounds are with a y. My thickness is a dy. So I have to rearrange this so that I have a function of y. So I am looking at pi times the integral from 1 to 2 of e to the y squared dy. I just cannot get that to stay in focus today. This is a trick that is helpful so many times when we're integrating things. Just kind of to keep in the back of your head. If I have e to the x squared, that's the same as e to the 2x. And so being able to go back and forth between those two things, whichever is the most convenient for what we're trying to integrate, is super helpful. So in this case, I think we'd be better off writing this as e to the 2y to finish off the integration. So if I rewrite this to say 1 to 2 of e to the 2y dy, then when I integrate that, I will get e to the 2y over 2, going from 1 to 2. So when I plug in a 2, that'll be e to the 4th over 2, minus when I plug in a 1, e squared over 2. Make sure my pi belongs to both of them. There's not a lot you can do with that. You could put the e to the 4th minus e squared in one numerator, but other than that, there's not a lot you can do to it. There's a great question in the chat, and I haven't thought very well about how I'm going to manage to do this both for the folks in the room and the folks on Zoom, but I'm going to do my best here. So don't try to take notes on this because I don't even know how you would take notes on this. I'm just going to try to offer a visualization of where that r squared is coming from. Yeah. Okay. So I'm going to draw really big and hope I can make something work here. So the region that we were working with on this last problem had y equals 1, and then we had this curve, and y equals 2. So that's like the thing that we were working with. And I drew in this arbitrary cross section. but we're in 3 dimensions, so I am going to use a really cheap visual aid. Sometimes I get this pretty good. We'll find out. Okay. See how I did. I'm a little long. Sweet. There's my arbitrary cross section. Okay. So I've got this arbitrary cross section and we are revolving it around the axis, meaning I am spinning it around the axis. Oops. And then it would go through the paper on the other side. So if you can imagine, I took this thing and when I spun it around and then pushed it through the other side, what I end up with is a circle. It's just a circle that has some thickness. And that thickness comes from either the dy, if I'm rotating it in this direction, or if I had something the other way, the thickness would be a little bit of dx. But the formula that we end up with looks like the area of that circle times the thickness. And the area of the circle part is the pi r squared, and the thickness is either the dx or the dy, depending on the direction we've got. And then we do the calculus thing, which says, I'm going to add them all up calculus style with that cool summation thing. I'm thinking about it. I will mention, I don't feel like our textbook or this homework is nearly enough practice with this. Like, even if you were to do every single problem that's like this in the textbook, there are literally 8. There just aren't enough example problems. So in Canvas, I've posted a link to the problems from this section from the old book that we used to use for 17B, because it's got like 30 examples. So if you're looking for more practice problems, I've got a bunch of them in Canvas if you just want more practice, because I don't think this is enough practice. Okay, I'm gonna get my picture going too. And we're not gonna actually do all of these integrals. I just want to practice like setting them up. So here's y equals x cubed. Here's y equals 8. And x equals 0 is secretly the y-axis. So now let's actually ask some questions. So for all of these, we're just going to set up the integrals. By the way, just for the sake of time, I'm going to let us know that that intersects at 2, 8. Because 2 cubed is 8. So that's where they're going to intersect. So if I were to take this region and just ask you to find the area of the region. We're not going to finish it. We're just going to set up the integral. So if I'm going to set up the area of the integral, I could draw an arbitrary cross section that was a rectangle. Which function is on the top? And which function is on the bottom? And I would be going as far to the left as 0 and as far to the right as 2. If I were to ask to find the volume revolving around the x-axis. So to find the volume revolving around the x-axis, I know that I want to take my arbitrary cross section perpendicular to the x-axis. So these words, the revolving part tells me that I'm going to have a pi r squared kind of thing happening. And the x-axis part, the around the x-axis part tells me it's going to be a dx. I'm around the x-axis. I know it's going to be a dx. So I'm going to draw my arbitrary cross-section in like this. And then I'm going to say, am I spinning around one of the edges of the object? And I'm not. The x-axis is down here, and there's a gap between the x-axis and where my cross-section is. So I know this is going to be some kind of pi big R squared dx minus a pi little r squared dx. And then to actually find what those radii are, I start like with my pencil or pen, whatever, on the axis of rotation, and I go until I hit the edges of my cross section. So the first edge I hit on my cross section belongs to the x cubed function, and that's my smaller radius. If I start at my axis of rotation and I go all the way through to the far edge, then that far edge or that big outer radius is happening at y equals 8. So that's my function over here. And then both of these, I would take these cross sections as far to the left as 0 and as far to the right as 2. So both of these are going to go 0 to 2. And then I want to change it up and instead revolve around the y-axis. I want to make sure that I keep my picture big, and to do that, I'm going to go ahead and redraw my picture. You don't need to redraw the picture. I'm literally drawing the same picture. I'm just going to scoop this up. So when I redraw my picture here, y equals 8, y equals x cubed. I'm rotating around the y-axis. That around the y-axis part is telling me I'm going to end up with a dy. It's also telling me that my cross-section needs to be horizontal. I've got a little bit of dy for thickness. And I'm revolving around one of the edges of the shape. So I don't have a little r, big R. Or if you want to think about it, the little r is 0. So I'm just not going to write that part. So my volume is going to look like pi times my radius. So I start at the axis of rotation and I go until I hit the edge. And my edge function here is y equals x cubed. But I know that it's going to be a dy. So I can't leave it as y equals x cubed. I need to write that as x equals something. And my x would be y to the 1/3 power. So my volume here, I would have pi. My function would be y to the 1/3. That's getting squared, dy. And my cross sections will come down as far as y equals 0 and up as far as y equals 8. I do want to address one question that no one has asked, but sometimes comes up. When we're finding areas, if we take cross sections vertically or we take cross sections horizontally, we should get the same value. But when I'm actually taking a shape and I'm spinning it around a different axis, we don't end up with the same three-dimensional shape. So we don't anticipate getting the same volume. It might happen on coincidence or it might happen for a particular shape, but in general, when I revolve around a different direction, I just don't even get the same picture. We don't have the same object anymore, so we're not going to get the same volume. More questions either from the homework, or do we want more volume practice? More area volume practice stuff? Yeah.
Can we do the one with the square?
Yeah, totally. And you all are going to be stuck with my terrible three-dimensional pictures, but I'm going to do my best and might have to reuse some cheap visual aids. So, I am looking at, this is homework 10, number 3. And I will get that to focus in a second. So the base of a solid is a circle with a radius of r. So I'm just going to go ahead and draw a circle. And it has a radius r. That's my lovely circle. And the cross sections perpendicular to the base are squares. And we've been asked to determine the area of each cross section and integrate those to determine the volume of S. Good times. Okay. I actually in Dutton Hall have a bunch of these three-dimensional objects made, but I'm going to make do with what I have in the classroom at the moment. Cool. I'm going to make my circle a little bit bigger just for the sake of the visual part. You don't need to make your circle bigger. I'm just trying to have a visual aid for this. Okay, there's my circle. And I'm going to go ahead and put it on an axis so that I've got like something to work with here. And it doesn't really matter which direction we put our cross sections, but I think it feels more natural to have vertical cross sections. At least it feels more natural to me to have vertical cross sections. It didn't tell us which direction to do them. So I'm going to draw in a vertical cross section. And this is going to be a little bit hard to make visualized with the camera situation, but this object is, bear with me, pretend it is square and sitting perpendicular to my circle. So this particular square, if we think about it, has a little bit of thickness. And if I were to lay it down and think about finding the area of this square, I really just need to know the length of one side of it. And then square that to get the area. So the volume of this thing is going to look like the area of the square times the thickness. And I've called my thickness dx. So I've got to figure out an expression for the area of the square. Because I've done this problem I'm going to get us to the shortest possible path to the area of the square. We can use trig or not. I vote not. So I'm going to draw in my radius strategically. Because if that's my radius, then I'm going to call this the height. And I'm going to call this part the X value. And actually, that's not really the height, because looking at my picture, like this whole side would be the height. So for now, I'm going to write this in as like a Y. But I'm going to say that this entire part is a 2Y. So my square is really 2Y by 2Y by a little bit of dx. So the area of my square, based on my picture here, that area is 4y squared. And I just have to figure out how to write the y based on knowing that this r is a constant and writing it in terms of x so that I have something to integrate. So if that r is a constant, then looking at this picture, I know that r squared is equal to x squared plus y squared. Which is convenient because the area of my square is 4y squared. I can replace the y squared part with r squared minus x squared. And then I just need to figure out the limits of integration. So I'm taking these slices, and each slice I take is like a slightly different sized square, right? So when I'm over here, that's the 2y part, which makes a bigger square than when I'm over here and I just have this size squares. So I'd have all of these like different size squares sort of stacked up together. But my squares are going to come as far to the left over here as negative r, and as far to the right over here as positive r. They didn't tell us what the radius was, right? If he had just said the radius is 5, then we would have used 5 for the r. And this would look like 25 minus x squared. He just told us that it was r. So the best we can do is say that our limits go from negative r to r. Good times. By the way, just for fun, what if this problem said that your base was a circle, but the cross sections perpendicular to the circle were equilateral triangles? It's an exceptionally gross problem. We're not really going to do it. But what that would look like visually is, rather than like at each point on the circle, drawing a side that turned into a square, at each point on the circle, we'd have that side, but what would be sticking out was like the shape of a triangle. So if we stacked all of these up, you'd kind of have like a cone thing, because each of the cross sections would be triangles. The one in the middle being the bigger triangle, because that side would mean it had a bigger height. So you can make some pretty cool shapes by thinking about it this way. You could also have a base that was a square and make the cross sections perpendicular to the base, like semicircles. Scissors would have been good, but you know, we're just gonna that's a beautiful semicircle, isn't it? So my cross sections perpendicular to the base would be a bunch of semicircles. So you can have lots of different pictures like this, but really the most common, because the math works out nicely, is to think about these revolution problems where we're revolving. And if we're revolving, we're always talking about a circle with a little bit of thickness.
This one.
Yeah.
So the area of the square times the thickness.
Mhm.
Like in the last one,
We had the area of a circle times the thickness. Mhm.
So, because the area. So how does that change?
So anytime I'm spinning in circles, right? Because I have that word revolve. Yeah. And so when I'm spinning in circles, I've got essentially the base part in this case is a circle and the height is a little bit of a thickness. Here, we're taking slices. We're not spinning in circles. So here my slices are squares. And the thickness becomes kind of like the height times the area for my shape.